Okay, so then let us begin with our mock test 3 discussion. So just mention the topic. So this is mock test 3. Okay. Let's start with the first question itself, which again is seems a little controversial now that I just thinking about it 5 minutes back. So, but let's just write the question. Okay, so we want to find, so this is problem 1. Okay. Find all solutions. Okay, find all solutions to sine nx. So if you want to obviously solve an x, sine nx plus sine mx equals to 1. Where n and m are fixed. Okay, fixed in z. We want to solve in x. Okay. So let me just check once again. Find all solutions to this where. Okay. So let's see. So what have you guys done in this? Yes. So, okay, right. Did any one of them lead to a concrete description of x? Okay, so then let's just discuss the complex number method. Okay, so you can tell me then, Adish, because the usual method is there, but let's try then complex numbers.
I don't know if it will lead, but it will just bring everything down to 10x.
Okay.
Like it will bring everything down to sine of x or cosine of x, and that n will be outside. So then we can deal with that.
Okay, so maybe you can tell us a few steps at least to begin with, then we can get an idea.
I just wrote that sine of nx will be cis of.
Okay, so you're saying the e to the power of that thing, to the power I n x. Okay.
That might minus.
Uh-huh.
And m also I have written it.
Right, right. Yes.
So then I tried to use binomial theorem.
Binomial theorem, okay.
Binomial theorem. Actually, I have designed the formula for sine of nx and sine of mx where n is an integer. I have designed it like a series.
Oh, in terms of sin x.
Yes, in terms of sine.
Ah, but then you will get a huge equation, right?
That is what
Yeah.
but then
But that's not solvable. No, that's not. Yeah, yeah, yeah. Right.
bad.
Exactly right. So, but what you have derived is that is a very useful formula. Okay, so I'm not going to do the derivation here. Yes, that's a standard technique. So sine nx, sine, I'm not going to do it, but sine nx can be written as some summation, and these coefficients are also quite exact, but I don't remember them exactly, so I'm not writing it. Sine to the power n x, okay, and I suppose cosine will also come up, and this will be rather, I should say, k, and maybe n minus k or something like that, x. Okay, sin ns can be written in this way. For those of you who don't know this, please try to derive this. Okay, this is and the complex numbers is the method. Okay, very interesting, very useful formula, at least. Okay, but as okay, something. Okay, so the exact details are not important because that won't throw much light into it. But yeah, You can, so those of you who don't know, try to derive it. But yeah, that will not be useful because you will get like an n degree polynomial equation which you want to solve. So that's not very useful for us. So yeah. So what Rasufro said, I had seen his solution and he stopped there. And I think there is no kind of, doesn't seem to be a way to do this. Okay, in the sense that let's do the usual trigonometric way. So we get sine, but I had seen this problem in some competition and then I was trying to solve it and I could not do it. So I thought, let's put it in the test and so one of you would solve it. Okay. But let's see. So then you get sine a minus b by 2, sorry, cos, and this equals to half. Is that right? Yeah. And this is bad. Yeah. This is not good.
That's why I thought that like I was stumbling upon this. Like I just realized that in the first half minute that this is not going to work. So I thought that let's just to analyze the function by calculus methods.
Okay. Hmm.
Because when you differentiate it both the sides, you get a zero, and that is a positive sign.
You get a 0. Okay. 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 Okay.
So
That is there. That is
you can
another.
find that
Right. 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 Okay. But then, but what I want maybe to see is from here, can we say that the solution will be completely arbitrary? Like there will be infinitely many arbitrary solutions from what we have done so far. From this, just from this line, can we say that the set of solutions is like arbitrary?
actually I think we can because let's say let us just take this function x
Uh,
x of x equals sine of right now let us take it simple sine of pi by 2 minus sine of nx
pi by 2 sine.
minus of nx
Okay, okay, like this. Okay. Uh-huh.
minus sine of nx sine of pi by 2 minus sine of nx.
So that's just sine. This is 1. Okay.
So 1 minus basically 1 minus
Huh. Uh-huh.
nx.
Yes, yes.
We are able to produce like now we can no 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 why are you writing that here?
Okay.
I thought it's sine of pi by 2.
Huh.
Now we can use that a plus b a minus b form, and if we can prove that this is the sine of some like the sine of some m into x. So for every
Hmm.
m, so we can prove that there are infinite.
Okay, okay, okay. So you're saying from this kind of thing. So maybe you're saying, yeah. So you can maybe write it like this by 2, and then you have cos. No, but there 2 will also come, and you have to take care of that also. Yeah, but it's but that's the same thing as this more or less. So that is the same thing. But from, I just want to see if from here we can, and because this kind of, what I'm trying to say is that this kind of looks to me like sine x times cos y. Is that, yeah? Though that's not true completely, because like if I take uh, this as x and I take this as y, it's not true that I can actually do it. I mean, what I will get is that I certainly need x is bigger than y, and then I have n plus m n minus m equals to x. So x by y has to also be rational. Yeah. This is not, so it's like these x and y are not completely arbitrary, but it still seems pretty arbitrary, isn't it? I'll just come to the calculus thing to see if there are any insights there. But from here, what do you think? Anyone?
Yeah, I think we will get some specific m and n.
No, but n and m are fixed. right? Or are you saying something else maybe? Huh? Ah, okay, okay, yes, okay. So I think maybe I get what you're saying. Like, yeah, so this is fixed, right? N plus m and n minus m is a fixed number. So that's sorry, yeah, that's a good point. I think if I'm interpreting you correctly, yeah. This is you're saying, right? So this basically this is x and y is kind of k times x, k times, right? Right. So this is interesting, right? Because what you get is sine x. So this equation is just like this, kx, where k is some fixed rational number bigger than 1. Right? I think that's what you are saying. And mostly, I mean, any rational number bigger than 1 can be written in this way, more or less. I understand it's not completely true, but yeah, more or less. If both have, you can make, like, I mean, if you have a rational number p by q, then you can just multiply by 2, and then you can make 2p equal to m plus n, right? And 2q equal to m minus n, am I right? And you can, yeah, so that's like an arbitrary rational number in some sense, fixed but arbitrary. Like we cannot really say anything special about that. If nothing special is given about m and n, is that my point? Okay, so which is nothing is given. So basically, then this is equal to half. So now does it yeah, say anything interesting? Sin x times cos kx is equal to half. So that k is a rational number bigger than 1. So just try to think about this. I don't know how to solve this. Like even so if something like sin x times let's say cos 10x, yeah, this can be attained by this thing, right? You can find m and n such that this can be attained. Okay, is it possible to solve this? Is this solvable? Not solvable, you have to say find all solutions. Yeah, solvable. And how many solutions are there? I don't know. Well, how many meaning that there will be infinitely many eventually, but like the class, how many different types? I don't have much idea about this. It seems very arbitrary to me. Have you guys come across this kind of equation? Let's say just focusing on this sin x times cos 10x. Yeah. No, right? It's strange. Yeah. Okay, so I think that's what I can say in this problem so far. So let us just see what Adi. But then I have a I've slightly modified the question. It became interesting. Like it became doable, I think. So what Adish is saying is that you can differentiate this, but even then, I don't see what happens if you do it. So then this becomes m times minus. Yeah. So then, yeah. So maybe if I differentiate it again, don't know if that is useful. No, so what is the derivative of cos? It's minus sine, right? But that will not matter. Ah, so then I can replace sine nx in this. Please correct me if something is going wrong. Immediately say it so that so this becomes minus m square by n square. You get this, right? And then you get, so this is something I think, right? So this is n square. Sorry.
Like we are getting something.
Yeah, this is actually interesting. I don't know what is happening, but something interesting is happening.
Actually, just doing some.
That is true. I'm not so much into the graph because we have to find the solutions. Okay. But yeah, that can certainly be tried. Maybe if we will have to try that. Hmm. Yeah, but this n square by m square. No, you can take arc sine, but 1 minute.
Obviously, like let's say that n square minus
Uh-huh.
obviously we need to do
Uh-huh. Right, right. Uh, uh,
reverse it by the
yes, but this may not be less than one. But that you have to that has to be in the question then. That's not our fault. Is that right? So it has to be in the question that this is less than one, right? Oh, sorry. Okay, why? Oh, yeah, 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 yeah. Yes, yes, yes. What am I thinking? Yeah, yeah. So then that gives something interesting, right? So then what does it say? That is then that's something very concrete because then this has to be equal to one, and then m is zero.
actually I did not.
No, yeah, because you see this is bigger than one, right? Yeah,
Obviously.
in the modulus even. Yeah, the modulus of this is so. Let's assume for a second, just to simplify thing. It doesn't matter. So I'm just this does not matter. It's good to assume this. Yeah, if we assume this, then then we are getting that. Yeah, sorry. So what am I saying? Yeah, then basically this it cannot be less than one, right? This is bigger than equal to one, right? Even if m is negative because it doesn't matter. So then it means that m is zero, which is a contradiction. So it's fine. Then we can say there are no solutions. Yeah, then and it's not a big sub. I don't know, but n and m are integers, so that's why it's like this, right? So then there are no solutions. um, yeah, yeah, that's right. Because even if you look at this, it also says the same thing, right? So this is less than one, and this is also no. So that is not necessarily less than one. Yeah, yeah, we can take the reverse thing and have the same thing, right? Yeah, right, right. So then are we getting that there are no solutions? Finally, right? Because as we Rashifru said, if it's bigger than they just take the reverse, and it doesn't matter because it's a symmetric equation. If there is solution with that, then solution. And then n equal to m. Mhm.
Like, like we are getting from here we are getting any
No, but then you see, if m is equal to 0, you put it in the last equation. There is a problem, right?
like you put in last
The very last one on the right. So then you get a problem, yeah. So I think then this is, I don't know.
do that
Yeah.
it should not be zero, but there should not be
Yeah, that's what I think. But here I've assumed that n is different from m. If n is equal to m, you can do that case separately. That should be easy. That I'm not doing. That is trivial, I think. I mean, that case we have to take, right? N equal to m. That will give some solutions, I hope. I mean, that will give, right? So Uh-huh.
Plastic, it is not consistent.
So what are you saying, Rasubro? I didn't understand. Uh-huh. Right. We get sine nx. Right. Uh-huh. Yeah, exactly. Yeah, that's something is wrong. That's what I was thinking. Yeah.
Actually, but can do that, but somewhere in the story, like it should be consistent.
No, no, but then finding solution is then that's no question of consistency in the sense that then something there here is wrong because if there are solutions, because here also we can take n equal to 1 and m equal to 0 and we are finding solutions. So then this proof is wrong somewhere. So let's see what is wrong. So and cos that's what I was thinking. So mine because looking at this was looking like there should be solutions. In fact, lots of them. Sorry, let's just have a look.
That should be plus actually.
This should be plus. Hmm. Ah, third step is wrong. Ah, that's what, right? So that's what this should be plus, right? And then, but then there will be no one here, right? So how am I writing all these things? Yeah, yeah. So we are just sorry. Okay. So then we get no, sorry. This one. No, wait. So why is it wrong? Wait, let's just remove this. So what I did is I substituted this one. So no, yeah, same thing, but let me write it like this. Yeah, but here I am using that both like n is not 0. So let me write that because that's what that was probably. So then I can put it in the equation. In the first equation, then I'll write 1 becomes minus m square by n square sine mx. No, so this is right. Okay, right. So that was right, but only that here I'm assuming that n cannot be 0. Okay, and the counterexample Rasulu gave is n was 0, basically m was 0, same thing. So that 0 case you have to do separately. Is that fine? It seems like that. Okay, but let's just see. So this is 1 minus. This is what I had got earlier, right? But the 0 case you have to do separately. 0 case and equality case. That you do separately. Other than that, there seem to be no solutions. And so then also you're finding, yeah, then also we have solutions. So then where then where is this wrong? Yeah, exactly. That's the thing. So then let's, yeah, and that, ah, No. But that is the thing. That is the thing. It's not a functionally true. It's not functionally equal. Sorry. No, but we have to just find the x, right, for which this happens. Good point. Good point, Chandan. So, so yeah, I think we are doing. Yes, yes. Uh, no. We are solving an x, right? So whenever it said solve, you're solving an x. Okay, that I said, I think in the beginning, but maybe, yeah. Solve an x. M and n are fixed, right? Solve in x. So there is a fundamental problem with differentiating both sides. So that's a very good point, and I kind of never thought about that. Point is that this equation number one, this equation, we don't know if it is true for all x, right? And unless it is true for all x, or unless it is true for a point and the entire neighborhood around that point, then how can you say that both sides are the same functions? Yeah, the LHS and the RHS in equation 1, these are equal at some specific values. Mostly it will be equal at some discrete values, right? But that doesn't mean that these two are equal as functions. And unless two things are equal as functions, at least even in locally, but at least somewhere they should be equal as functions, some neighborhood, you cannot differentiate both sides. They will not have the same slopes, let's say. Right? So you can differentiate an identity, but you cannot differentiate this. Yeah, I mean, you can differentiate, but then both sides are not equal. Mm-hmm. No, because those are only points. So when you differentiate two things, then what are you doing? So when you differentiate, let's say fx is there and gx is there. What does differentiating mean? You're saying that fx is equal to gx. Let's say fx is equal to gx at some x naught. Yeah. Does this imply that they will have the same derivatives at x naught? No. Why? Yeah. No. Yeah. If two functions have the same value at a point, yeah, like there is some x for which sine nx plus sine mx is 1, some value at a point. That does not imply that the derivatives will also be equal, right? So you cannot differentiate. So it makes no sense to differentiate unless you are given that, fx equals to gx on some interval, or there are some other weaker conditions that can be given, but let's not think about them. But these two functions locally don't need to have the same slope at x naught, so you cannot differentiate. All right, good. So it makes no sense to differentiate. It looks like the question is very arbitrary. Okay, good point. So that was a very important point, I think. And this is a very sneaky thing because we are so used to just differentiating both sides. But then I thought that we can just change this equation and then try to do something. Okay. So I just thought maybe so, and this is homework. You guys should try this for homework because I kind of have solved it. Uh-huh. Yes, but we want the solution in terms of n and m. Like for an arbitrary n and m, can you find what x's will satisfy this? Can you find a formula for those x's in terms of n and m? Right, and that seems to be, that seems to be hard or maybe impossible. Uh, No, not any n and m, but any n and m that is given, find all the x for which it's 1. So obviously that x will depend on n and m. Right, but is there a formula? Something like that. So I don't know. Okay. No, I think for all n and m, there will be some solutions at least. Right. That is also seems to be true. But like a formula. So it's like x is equal to n square plus m square by something, 2m. Is there a formula like that? Or something that seems to be impossible to describe as a formula. And that is okay. Sometimes things are impossible to describe. So I mean, this is some doable versions of this question are okay. Maybe I can say, are there infinitely many solutions? Are there infinitely? Oh, sorry, there are infinitely many solutions always. No. This is not what I was saying. Sorry. Yeah. So let me. This equal to 0. One question. Second question equal to 2. Please try this for homework. These two are good easy questions. One of them is easy. One of them is a good, very easy. Yeah, that is just equal to 2. You should try. It's a good question. Okay. But then solving it, you'll see that there is some interesting thing, because n and m are not just yes, that's right. And yeah, but the finding x will require some number theoretic analysis, something like that. Okay, because something think it's not directly LCM, but just think. Yeah, I mean, you can even just say that x is between 0 to 2 pi and then do this problem. Then you understand that there will be finitely many solutions, right? Because I mean, eventually this is just a curve and it cannot cut the line. You cannot cut this line infinitely many times, that in the small interval. That just seems impossible, right? So it will have finitely many solutions, but find them. How many are there? That's more important actually. How many are there was the, but maybe yeah, or do how many in that interval. Otherwise, you can just say infinity and go go home. Okay, this is a good question. Trust me, this is a doable question. So with that, let's move to question 2. Okay, this is a big mess, but I think we learned a few things. But yeah, just try this. Maybe they intended to make it 2 only. Uh-huh. Yes. Uh-huh. So though there's one. Okay. So they may update the date. That's okay. It will be there for some time. So don't worry. Yeah. Yeah. Okay. So the form has come out. I did not know that. Okay. Okay. Now let's do the next question. The next question, let's see how to do this. I don't know, but this was a very interesting question. That this was made by me, but it turns out it's a very interesting question. Means this it existed earlier also, but yeah. Find is what I made it up on my own, but then I found it's existing. Find all two variable. Find all two variable f x y such that. So I'll just come and just drink some water and come. Just try this. Means I've already tried this, but go to 0. So basically, yeah, and this is, you see, for all theta. Okay, for all theta in R. So you want a two variable polynomial that vanishes at cos theta comma sin theta. So obviously you know some examples like x square plus y square minus 1. Yeah, but what are the others? Describe all of them. Okay, so I'll just come and do it. Try to do it. Okay. Yeah. So anyone would like to say what they have? Yeah. Sorry. Say again. One by one polynomials. Hmm. Okay. So you're stealing some polynomial. Okay. So say. Hmm. 1 by x square. Mm-hmm. Oh, so this is, but this is not a polynomial, right? In x, because x is in the denominator. You see, I mean, yeah, I understand that this is also an identity. Like this function will vanish at cos theta comma sin theta. It's good, but that's a bonus. We don't want these functions because these are not polynomials. Okay. Oh, no, I have mentioned polynomials, right, in the question. I have not written, I wrote it now, but yeah, we want polynomials. Okay. Otherwise, it becomes very arbitrary. So this, okay, so that's true. Implies that f of sine theta, because since it's true for all theta, and that's a good thing, right? Since it's true for all theta, you can put something, right, pi by 2 or some pi by 2 minus theta and get that this must also be true. Okay, and so this is a very good, maybe but no, so that does not see this itself does not imply that f is symmetric. No. Think you're only getting it for these values, right? For cos theta and sin theta. For yeah, so what you have got is that f of x comma y equal to f of but this is a two variable polynomial. One at a time. Someone so say Brasur, you say first. No, so 2-degree polynomials are not determined by such things. No, that's not true. In fact, I can give you a non-symmetric polynomial. Okay, so I can just give you a non-symmetric polynomial. You can take x times, you can take this. Yeah, you see, it's not symmetric. Okay. So one variable polynomials obviously, but two variable polynomials it doesn't work. So yeah, this you're not getting. Okay, you're only getting it for infinitely many values, but they don't determine. But yeah, I mean, you're right, but there are some infinite sets which determine. Okay, so that's a little tricky thing. I'll not talk about it now, but I'll say that later maybe. So Adish, you were saying something? Okay. So do you have a different reason? Or why? No, why will it be satisfied? That's the thing. Huh? For all x. For all x and y. Yes. Yes. So yeah, that is certainly correct. But so as mentioning these things, something comes to my mind. So maybe I can ask that here. if f of x comma y, or maybe I can say like this, if f of x to the power n no, sorry, that is doesn't work. Leave it. Or maybe no, leave it. Becomes difficult, I think. So what are the other two variable polynomials? We have seen one. Much larger. That's right.
I think that is
Which do not satisfy. Uh-huh. 4x square y square plus 4 into 2x square minus 1. This whole square. Wonderful. How did you get this? Okay. Okay. Right. Something. Okay. So is this the right equation I've written, which you wanted to say? Later, outside. Okay. So we can just forget about the 4. Means I understand you got it through that only, but now here is the thing that you guys try. Can this be written in terms of x square plus y square minus 1? Can this new, which looks like a new polynomial, can this be written in terms of f? Give this a thought. So I'm asking you guys to just try to factorize this. Can you factorize this polynomial and somehow get x square plus y square minus 1? Yeah. So if you just expand, you will see. So there's no delicate factorization here. If you just, I think. Sorry, so maybe there is some noise. So there is a festival today, Shivratri. So we have a temple here. So they are praying this, and then you can get this. Okay, so you see, in some sense, this is not a new example. Okay. Oh, sorry. So no, it is right. Just check. 4, 4 is here, right? Oh, so what to do with the 4? So maybe then maybe there is no 4 here. Oh God. 1 second, just 1 second. Sorry. That's what, something like that, yeah. But yeah, something like that. When you calculate this, you will get that it's again a multiple of, because I know there's no but something like this you will get. Okay. So you see, the most obvious examples were the set of all So this is real polynomials. I have also mentioned that, I think. I didn't mention that for simplicity, but anyways, just let's not mention anything. Yeah, let me just write here. Okay? This real polynomials, the set of all real polynomials times this f which we wrote in the beginning, or which, yeah, the canonical f, the most natural f. These all are examples. Is that right? Whenever you have a set and you have a polynomial which vanishes on that set, then all multiples of that polynomials with other polynomials also vanish. Is it good? Yeah. So all these things vanish at cos theta comma sin theta. Vanish, I should just say vanish on the unit circle. Okay, vanish on the unit circle. But really the question is, are there any other? Are there any other polynomials? Okay. So how would we attack this kind of situation? So what happened? Initially, we started with a set X kind of, right? Initially, we started with a set X or maybe C circle. Initially, we started with this set cos theta comma sin theta. Yeah. We found all the polynomials that vanish on it, right? We wanted to find all the polynomials that vanish on, or maybe I should say not like this. I can say that you start with x square plus with this, because this is a very interesting point. A lot of the difficult questions in polynomial theory, you can at least guess what the answer will be and then try to prove it by this kind of heuristic. It's just a heuristic in the sense, what is happening is you're starting with this polynomial and then you're looking at the zero set of this polynomial. You get this, you know that this is exactly cos theta comma sin theta. There's nothing more. And that also we know. So this is a very good polynomial in the sense that it is the zero set is exactly this cos theta comma sin. So you start with a natural polynomial and you take it zero set, right? Now when you try to, so this is like you started with algebra, which is algebraic expression, right? And you got a circle, the geometry. So you go from algebra to geometry. Now you are trying to ask, okay, what are all the polynomials? Maybe I can, yeah, so maybe I should write, yeah. What are all the polynomials that vanish on? What are all the polynomials that vanish on this? Okay, on this set, yeah, which is cos theta comma sin theta. Yeah, so certainly the natural candidates for this is this, the polynomial that you started with, that will obviously be there, but this times any polynomial, these are certainly there. Yeah, this is called the ideal set of it, but this is the thing. Okay, and then usually what will happen, it doesn't happen, and when it doesn't happen, you would know there is some simple way it doesn't happen. You will see that there is actually equality. Okay, so you understand that these polynomials certainly vanish. Okay, so you're recognizing your this thing as a zero set of some standard polynomial. Okay, and then you take the zero set, and basically what we are asking is the reverse question again. Okay, coming back to the algebra. And so the claim is that you come back precisely, meaning that you don't get any more polynomials. You get exactly this. Okay, so here the answer is no. I'm telling you guys this. Now try to prove. I'll give some hints. I'll try to give some hints maybe. We'll see. Okay, so let's first see if there are any questions so far here. This was just a heuristic. Okay, that you start with the standard polynomial which vanishes on it, exactly vanishes on it. Okay, and then show that there are no more. So the others are just multiples. Okay. Okay. So I think these appear Chebyshev polynomials or something if this is there, but this is not Chebyshev polynomial. But maybe I don't remember what question you're saying. But yeah, no, this is a very general idea. These are very interesting ideas because yeah, they are simple to understand, but to prove it general is difficult. But we don't have to prove it in general. We have to just do some function. Mhm. Okay, okay. That would be slightly easier maybe. I don't know. Yeah. Hmm. No, that is a different, slightly easier. Anyways, yeah. So here the claim. So here the claim is if g vanishes on this. So if g, let me just write it in full. Okay, if g of cos theta comma sin theta is equal to 0 for all theta in R, then what we want to show is g of x comma y is equal to this times sum and no remainder. In that sense, this is what we want to show. Okay. So how would you now reduce this question to sort of maybe single variable or something like that? How would you show such a thing? So we cannot, that's the problem. The problem is that we cannot do this because, no, you're right. I mean, there will be some remainder, but it will not be unique because this is not a one variable situation. Okay. But this is the right track. So can you describe the remainder somewhat? Otherwise also not very useful. So can you describe the remainder? That is the challenge. No, that is not true. Just think, because you can have high degrees of y or high degrees of x. You cannot, I mean, like, you understand, right? You cannot really group that out into x square plus y square. Like if it is just y to the 10, then how can you extract that into x square plus y square minus 1? Right. You cannot reduce this further if the situation was like this. But yeah, you can somewhat play a game. So in the sense, let's say that you can write this, let's say that there is a polynomial in y, completely in y, and then you have some x and then a polynomial completely in y again. I'm just breaking it up and writing it like this, right? I mean, any polynomial in two variables can be written something like this. Then you have x square and again a polynomial in y. And I mean, let's just stop at 4 degree for a second and see. You guys agree that, I mean, in fact, anything can be written like this, right? Okay. Anything can be written like this. Now what can we do? I want to make groups, and so that I can remove the x square. If there is something, if I can take out some x square plus y square minus 1 from here, I will be happy to do it. That is the point. Right. So if that is the case, then I can say, well, okay, then I will add to this thing, and I have to subtract, obviously. And then I can just and you see why I'm doing this. P3y and add a P3y. And then I can, you see, I can then take away this thing. This, and this. I can take it away from the remainder and put it in the first part, in this part. That's the meaning of, that's what division is, more of a grouping in the first. So it will become H plus P3y. Right? And then this will become, you will end up with, so you won't completely simplify the thing, but the point is that you will end up with more y's, only y's. You can do the same thing with this. You cannot do it with this, I think, but you can do it with the higher powers. Even if it's x cube, sorry, I should have written. You can do the same thing. Okay. So the point is that you can not do a complete division remainder and there is no unique remainder. Okay. But you can do this grouping. These are very important techniques and they look very ad hoc, but they are not. They look ad hoc because we don't have a good language to do algebra now. We are doing it just like using the good old things. Okay. But the point is, the upshot of all this is that eventually you can say that the remainder is just this. Right, because I mean, these things are again just polynomials in y, so you can put them here only. Right. So the remainder is just a polynomial in y plus x times another polynomial in y. So this is a kind of an extended version of division remainder. We don't need uniqueness, that's fine. We don't have uniqueness, it's fine. We don't have uniqueness, so that's fine. We can do with what we have here. Yes. Yes. So after this, you have to just do some kind of manipulation, which kind of you are doing in the beginning. Putting theta equal to minus theta or theta equal to pi by 2 minus theta. Okay. So let's just slide the remainder in this form. Okay. So this is the technique first. And one can say this in terms of, just one second. Yeah, anyways, I don't know actually. Yeah. So to get to the thing, real thing, we can say this is P1 times X times P2Y. Good. Now, what do we want? Now, basically, we want, that's the reason why we did this is we want this to vanish, right? Right. So basically, you want this polynomial to be 0 for all theta, for all x. I mean, better to just write. And this looks even wrong too when you look at it, and it is wrong, you can easily prove. In a sense that this cannot happen for non-zero polynomials. Then we will have to have this. And that's why we were doing all this manipulation, right? Taking the equation modulo x square plus y square minus 1. Taking g modulo x square plus y square minus 1. Okay. So No, single something you can do, yeah. Or you will get some cases in which maybe P1 equals to P2, or then you can put some other theta, just do something you can do. It's so simple. From here, it is just manipulation. Yeah. So some manipulation, just basic polynomial functional equation question. So this is like a polynomial functional equation question. Okay. Manipulation will give that P1, P2 equals to 0. Okay. So I think this is a wonderful question in that sense. Right? But the gentle idea in was very interesting. That initially I started with a polynomial, some polynomial, any polynomial you start with, not this necessarily. You take the 0 set of that, and then you again ask for all the polynomials that vanish on it. Okay, certainly this will contain all multiples, but will it contain more? And there's a general theorem that says, and this we cannot prove, I think. Maybe if I will think, I can say it in elementary ways, but not good to say now. If f is irreducible, at least. Okay, if, and it's 2 variable, 3 variable, any variables. Okay, if f is irreducible, then yeah, then true. Then this is true. Now, again, what I did is start with a polynomial, some irreducible polynomial, take it 0 set, and again go to ask the algebra back. Can I? So you start with the polynomial, you take the 0 set. That's some curve, right, on the plane, 0 set. In our case, it was just a circle. So that's geometry. From the geometry, you ask, can I recover back the algebra? And the answer is yes. It is just f, basically f again. Okay. And this is the first theorem in algebraic geometry. That is what algebraic geometry tries to do. How much of geometry can you understand from algebra and vice versa? And it's mysterious how we can know so much from one from the other. And that is algebraic geometry. You guys may have heard that name. CMI is very popular for that. CMI is one of them. I mean, I don't know any algebraic geometry. Okay, this is just some pop thing I'm saying. Okay, but yeah, that is the thing. Yeah, no. So point is that this is true. No, so the question that this is true in the complex world. This is true in the complex world always, and that's theorem. Okay. What I was exploring once for some other purpose was when it is true in the real world. Okay, because in the real world, this is not always true. You can see, I mean, because you can, I mean, yeah, because you can simply start with x squared plus 1, right? And then you ask for the 0 set is empty. But then you ask for what polynomials, vanish on the empty set. You understand, right? You don't get back x squared plus 1 multiple of that. You can get many things. You see, so it's not true in the real world always. But when is it true in the real world? I was exploring, and so this is one case in which it is true in the real world also. So in fact, what we have done cannot be done even by quoting some advanced theorem. It has to be done like this to some extent. Okay, so just the 0 set are recognized as the 0 set of some polynomial. Then you go back and you ask what are all the polynomials that vanish on that, and you get exactly that same thing, multiples with a natural, because multiples of it will obviously be there. This is always true in the complex world. When it is true in the real world, because here we didn't use anything about complex, remember, we were in the real world only and we proved this. Okay, so that's why this question is very wonderful. And then there was some generalization, but that's for later. Okay. So these are 2 questions we have done. Yeah, I'm sorry. So I have to stop today. Okay, because today I have to stop at 10:30 only. Okay. Next time, so 3 and 4 are very simple. Okay, I mean, I think they are simple. Okay. Next time I'll finish this. Okay. What is interesting here is question number 8. There we will have to learn something. We'll learn some very good method again, which you can, yeah. And 10 also. I don't know if one of you have done it. I think someone had done it. You were, yeah, you were, right. Yes. Okay. So I'll just quickly do this the next time and we'll do more things. Today I'm just stopping rather before time. some sense. Okay, so yeah, okay. Next class will be tomorrow. Okay, tomorrow I will take a class. I'll do this, and then I think I'll get some time. Then I'll do some integration problems, and not this time I won't do the theoretical ones. I'll try to do the more interesting problems. Okay, yeah. But last time what we did is also useful, so don't underestimate that. Yes, that's a plan for tomorrow. No, again, no new theory, no new topics tomorrow, but completing this and doing the integration, some integration.